This is section 13.4 and this is example 1. So this is our introduction to Green's theorem. And what we have is a line integral where C is a triangular curve consisting of the line segments from the following points. So what we're going to do is we're going to just quickly review from 13.2. Let's say we did not have Green's theorem available to us. Let's say that we want to use the fundamental theorem. We would double check here that this is not conservative, but if it is conservative, then certainly the fundamental theorem is much easier. So remember, we have P and Q. The derivative of P with respect to Y is 0, and the derivative of Q with respect to X is Y. And so because these are not equal, then we are not able to use the fundamental theorem of line integrals. So let's say that we want to use techniques from 13.2. In this case, we have a little triangular region, and we go from 0, 0 to 1, 0. So that's our first path there. And then we go from 1, 0 to 0, 1. And then we go down back to the origin. Okay, so this, remember, just positive orientation. This is counterclockwise, so this is positively oriented. But again, we're going to go back to 13.2 briefly. Let's pretend like we have never seen Green's theorem, and we're going to calculate by taking each of our three different paths. So our red path, we're going to go from 0, 0 to 1, 0. Our equation is y equals 0. And our integral then would be from 0 to 1. These are x values, okay? We have x to the fourth dx. So I'm back here in the line integral. So x to the fourth dx. Since y is 0, this entire second portion is 0. And we are left with the integral, or the antiderivative of 1/5 x to the fifth from 0 to 1, and we get 1/5. So that is, let's call that C1. Okay, then we're going to do C2, and C2 is going to be y equal to 1 minus x. That's the equation of the line there. We have, let's see, x values from, in this case, remember the order we're going in, so it's going to be from 1 to 0, because again, we're going to start here. We're going to go this direction, so it's going to be when x is 1 to x is 0. And then we have x to the fourth dx plus x. And again, I'm back here, so if we have x times y, y is 1 minus x. So it'll be x times 1 minus x. And then dy is equal to negative dx. So that's going to be multiplied by negative dx. All right, so that's our integral. Let's go ahead and simplify this integral. So we have the integral from, I suppose we could change this. So from 0 to 1, we'll make it negative. We have x to the fourth plus x, actually minus x, plus x squared. Just remember, we got to distribute this negative. I almost forgot that. And then we have dx like that. Okay, so let's do the antiderivative. So we have negative 1/5 x to the fifth minus 1/2 x squared plus 1/3 x to the third. And we're going to evaluate from 0 to 1. So we have negative 1/5 minus 1/2 plus 1/3. And then the last one would be 0, so we don't mind about that. This gives us negative 1 over 30. Okay, and then last but not least, we have C3 up here in our diagram. And C3 is when x is equal to 0. And if you notice from the original line integral, if we're looking at the integral of x to the fourth dx plus xy dy, if x is 0, this whole thing is 0. So that's nice and easy. Okay, so what we have then for a final answer is going to be 1/5 from, this is C1, and minus 1 over 30 from C2, and C3 was 0, and so what we get is a grand total of 1/6. So that is essentially the old method of doing line, or not the old method, but one of our methods that was prior to this for line integrals. This is from section 13.2. So because in this particular case, we have this, this positively oriented closed curve, then what we're going to do is attempt to use Green's theorem. So let's go back here for a second, and we're going to just draw this out one more time. So we have this triangle here, and this region right here is the region D. And Green's theorem says that we would take the double integral of D of dq dx minus dp dy dA. And we had already calculated dq dx and dp dy above, and dq dx, let's just go up to that really quick, was y, so I'm just looking at this portion, so dq dx is y and dp dy was 0. So what this becomes is just the integral, or the integrand of y. And let's go ahead and just choose the order dy dx to substitute for dA. So the inside integral is going to be in terms of y. And if we look at our region, and this goes back to chapter 12, so the minimum y is 0, and the maximum y is that line, which is just y equals 1 minus x. And then the outer integral is x, which is just 0 to 1. So in other words, what we're doing is we're setting up Green's theorem, and then from Green's theorem, we're going back to everything we learned in chapter 12 to do a double integral. So our double integral will get the integral from 0 to 1 of the antiderivative, which is 1/2 y squared, evaluated for y is 0 to y is 1 minus x. And we get 1/2 times the quantity 1 minus x squared, which is 1/2 times 1 minus 2x plus x squared. And then we'll simplify one more time. So we have, let's see, 1/2 minus x plus 1/2 x cubed dx. And the antiderivative is 1/2 x minus 1/2 x squared, and plus 1/6 x to the, oh, hold on, I made a mistake. This is x squared here. Sorry. So that would be x to the third. And then we're evaluating from 0 to 1, which gives us a grand total of 1/6, which is the same answer. So you can see that Green's theorem is a little bit of a shortcut for us, and it works nicely if the problem allows it. The next video will be on examples 2 and 3.